Welcome back, guys, to Urban Odyssey. This is going to be the fourth section of the 6G white paper breakdown. We're going to get into it in just a moment. Thank you guys for tuning in. Alrighty, guys, let's get into the fourth section of the 6G white paper. This one is titled Intelligent Communication Environments. The last section was on terahertz band frequencies, and now it's going to get into some more of the idea that they have issues with, getting the beams to go in the direction that they want them to go in. And so they have something called beam steering, and that's kind of what this is going to get into. So if you haven't seen the first three parts, I highly suggest you go back and check those out, because this does build on itself, and you will probably need the first 3 and 4 after this video is complete sections to fully understand the later parts of this paper. So all right, let's get started. Intelligent communication environments. Along with the rapid growth in the number of wireless devices, services, and applications, a corresponding demand for higher speed wireless communications has burgeoned in the recent years. Nevertheless, the major challenge at millimeter wave and terahertz band frequencies is the limited communication distance because of the remarkably high path loss inherent to small wavelengths and the limited transmission power of millimeter wave and terahertz band transceivers. Current solutions primarily focus on the advancement of wireless transceiver hardware and software, as well as network optimization strategies. However, the wireless propagation medium has been largely neglected. The wireless communication environments for both indoor and outdoor scenarios can be actively used in order to become controllable for signal propagation. To control signal propagation in environments is essentially to control how electromagnetic waves interact with scatterers, which include indoor furniture and outdoor buildings as well as other infrastructure. Typically, the controllable behaviors of electromagnetic waves include controlled reflection, absorption, wave collimination, signal waveguiding, and polarization tuning. Let me go ahead and highlight that for everybody, and then I'll show you I think the figures on the next page. I'll read that again. Typically, the controllable behaviors of electromagnetic waves include controlled reflection, absorption, wave collimination, signal wave guiding, and polarization tuning, as illustrated in section 4. The notion of intelligent communication environments resides in the control algorithms, where deep learning and reinforcement learning are to be exploited to dynamically configure the environments. In the following subsections, we elaborate on these controllable wave behaviors, current research efforts, as well as corresponding open issues. Let me see if figure 4 is on the next page. I think it is. Yep, here it is. This is figure 4 that it just referenced. Let me zoom in on it. There you go. So figure 4 is titled Conceptual Design of a Plasmonic Reflect Array Able to Unconventionally Manipulate EM Waves. And see, A, B, C, D, and E are A, phase shift, B, wave steering, C, absorption, D, collimation, and E, polarization modification. And it shows you these different planes: metamaterial planes, sensing and actuation plane, shielding plane, computing plane, and communications plane. So the first subsection, basics of intelligent communication environments. The intelligent environments can be seen as a three-dimensional structure with several layers, each with different functionalities. Recent research under the EU research project VisorSurf has demonstrated a structure with 5 main layers, which are, from top to bottom, the EM behavior layer, the actuation and sensing layer, the shielding layer, the computing layer, and the communication layer, respectively. And I will highlight that. And I think that's basically what that image just was, that I just showed you, figure 4. Specifically, the EM behavior layer is composed of meta surfaces. And let me pause on that real quick, just because this is important. What does meta mean? Well, I mean, obviously, Facebook, it used to be Meta, and then they changed their name to Meta. So it's not talking about Facebook. I'll tell you that right now. Let me see if I still have the image saved. That's what I'm looking for. Yeah, here it is. 1 second. Let me show this to you. Yeah, so meta. What does meta mean? Well, in Hebrew, it turns out in Hebrew that meta means dead. Huh. Well, so be very clear on this, and just, if for the sake of, if you're listening to me speak, whenever you hear meta, and now that we know that meta means dead in Hebrew, basically just think, the afterlife, hell, something like that, because pretty much all of this 6G stuff is what you would expect in hell. To be sprayed with nanomaterials and be put into an animal farm. So that's just my personal definition. You don't have to fully agree with that the same way, but that is the subtext for when you hear me say meta. Okay. So specifically, the EM behavior layer is composed of meta surfaces, and you're going to hear that pop up a lot. A two-dimensional representation of meta materials, and has a tunable impedance to control directions of reflection of the EM waves. So other works use reflect array antennas as the top surface. The actuation and sensing layer consists of circuits for phase shifting and sensors for impinging signal sensing. Some options for actuation include PIN diodes, PIN diodes with controllable biasing voltage as switches and reflect array antennas, and complementary metal oxide semiconductors, or CMOS, transistors, as well as micro electrical mechanical switchers or systems, which is going to pop up a lot. That's MEMS. And before I get too far, let me pull up the definition of that, because I do have a definition of that here. Okay, 1 second. Cool. There it is, MEMS. Let me read it for you. There we go. MEMS, micro electrical mechanical systems or switches. The inhalable infrastructure, often marketed as smart dust. These are not merely sensors, but air molecule particulates that function as a weaponized aerosol. They are designed to remagnetize and work as cohorts, effectively self-assembling into a wireless sensor network after being dispersed via aircraft, chemtrails, pollution. And remember, let's see, I think I've got that here too. Yep, remember? That right there that you're seeing, that's what it's referring to. Snow globe, fog, right there, smart dust. MEMS are capable of sensing light, temperature, vibration, magnetism, and chemicals, transforming the very atmosphere into an interior and the interior of a human body into a surveillance medium. Their simulation environments is cynically referred to as sugar or sugar MEMS, masking the reality that this technology turns the environment into a hostile monitoring entity. That it does. Okay, let's see. MEMS switches for meta surfaces. The shielding layer isolates. I'm starting back down here. The shielding layer isolates the upper and lower parts of the layered structure so as to minimize the possible interference. The computing layer serves to control the phase shifts and process sensed impinging waves. To this end, another reported solution makes use of the field programmable gated arrays, or FPGA, to fulfill such functions on meta surfaces. Finally, the communication layer connects all the upper layers. So let's see. Let me make sure I can highlight this so you can all make it out clearly. Okay, so the actuating and sensing layer. Okay. The shielding layer. Okay. The computing layer. And finally, communications layer. So it's all color coded for you there. I'll read through that one more time. The actuation and sensing layer consists of circuits for phase shifting and sensors for impinging signal sensing. The shielding layer isolates the upper and lower parts of the layered structure so as to minimize the possible interference. The computing layer serves to control the phase shifts and process sensed impinging waves. And finally, the communication layer connects all of the upper layers. And that's what you're seeing here. Figure 4. Which I'm kind of glad that we looked at that before I read that section. So, okay. And it goes on about the communications layer and serves as the gateway towards the central controller, which processes all connection requests, forwards and receives signals, and conducts the aforementioned controlled wave functions. So let's see. Top layer was the actuating and sensing layers. Let's see. So that was orange. I'll highlight it. Boom. Okay, the second was the shielding layer, and that was yellow. Boom. The computing layer is green. And the final was the communications plane. Compared to existing relays with multiple antennas, which are widely deployed in wireless networks, intelligent communication environments offer the following advantages. I will highlight those two. 1. A higher spatial diversity due to the wide coverage of intelligent surface with controllable antenna arrays. 2. A reduced processing time, giving that computing and communication layers are directly underneath the surface layer. And 3. A higher flexibility in networking or network routing when impinging signals come from different directions, and the intelligent surfaces are able to collimate waves and reflect them towards desired directions. Let's see, functionalities of intelligent environments. Let's see. Yeah, I'll go ahead and read through it a little bit. Bolstered by the layered structure, intelligent surfaces can enable controlled EM wave operations. Here's where I'm at, by the way. At micro and MM wave frequencies, metasurfaces are considered as a good candidate, while at the terahertz band, graphene-based plasmonic antenna arrays are desirable. Highlight that. Oh, there it went. In metasurfaces, a meta-atom is the smallest unit, which is a conductor with a size smaller than half the wavelength of the signal. Let's see. Oh. Let's see. With the size smaller than half the wavelength of the signal. Metasurfaces can thus control the impinging EM waves with a very fine granularity. The meta-atoms are interconnected by a set of miniaturized controllers that connect the switches of the meta-surfaces in the computing layer, while a gateway serves as the connectivity unit in the communication layer to provide inner element and external control. At terahertz bands, when the metasurfaces do not yield optimal performance, the graphene-based plasmonic antenna arrays serve as a promising alternative. So that's very important, because that's what the this right here is. I think let me make sure I know what that little Greek sign there is. I think that's gamma. Okay, so it was actually a lambda, and it's a sign for wavelength. So just to make sure everybody understands that, let me go back. There we go. So that's what this means right here. Okay, so compared to metallic antenna arrays, the plasmonic antenna arrays can have a much denser element layout and go beyond the lambda over 2, which is half the wavelength sampling of space, towards a more precise space and frequency beamforming. Owing to the physics of plasmonics, in our previous work we have demonstrated that graphene can be used to build nanotransceivers and nano antennas with a maximum dimension of 1/20th of the wavelength at terahertz frequencies, allowing them to be densely integrated in very small footprints. Let's see, 1,024 elements in less than 1 millimeter squared. That's pretty mind-blowing. Let me initially grab the definitions that I've got on Plasmonics and read those for you. Okay, this is a definition from the Devil's Dictionary that we've referenced, I think, in the last episode. Plasmonics. This is the field of study which explores and seeks applications for the physical phenomena which occur on a nanoscale in conjunction with the interface of a particular kinds of metals and dielectrics. Materials that serve as electrical insulators which become polarized when exposed to an electrical field and, among other things, can enhance capacitance or energy storage in electric circuits. So that's what dielectrics is. Materials that serve as electrical insulators which can become polarized when exposed to an electrical field and, among other things, can enhance capacitance or energy storage in electrical circuits. A plasmon is a quantum of plasma oscillation, and Plasmonics explores the properties of such plasma oscillations and how they can be manipulated on the nanoscale. These coherent oscillations are associated with electromagnetic waves that exist along the nanoscale interface that juxtaposes a dielectric and a metal. Various metals have different plasmonics properties, and artificially designed non-porous metals have an array of plasmonics properties. Plasmonics has potential ramification for biophotonics. Consequently, not only does plasmonics carry possible applications for such fields of study as optogenetics, which is the use of light to turn genes on and off, but as well, it raises questions as to how and to what extent biophotonics and plasmonics might adversely affect or suppress the health of a person's biofield. Okay, back over here. Okay. As shown in figure 4, therefore, by incorporating the graphene-based plasmonic antenna arrays at terahertz bands and metasurfaces operating at millimeter wave bands, we can expand the operational spectrum of intelligent environments and utilize them in transmission and reception in a controllable manner. Okay, so now we're in subsection C, and that gets into the different planes, and let me see if I can. Yeah, I think I'll color code these because we've been keeping that going. Maybe I missed one, I guess. I think I did the EM behavior layer of the metasurfaces, so that was red. Okay. So, that being said, metamaterials red. Sensing and actuation was orange. Computing was yellow. Communication. Wait. Oh, there was no shielding plane. There we go. Cool. There we go. So that should be correct. Yeah, okay. All right, let's get started on the next section. Layered structure of intelligent communication environments. So this is going to go over all of the layers. Based on the operating principles of the aforementioned intelligent communication environments, in this subsection, we anatomize the layered structure and detail each layer's functionality. 1. The metamaterial plane. The metamaterial plane is also the surface plane, as shown in figure 4. In designs based on reflect arrays, phase shifts are applied to each element to improve useful signals while canceling interference. The metasurface element proposed in citation 62 with millimeter scale dimensions is connected to a PIN diode with a bias voltage to control operation modes such as alternating polarizations. Okay, what I actually just went ahead and did was put the figure up on the screen to the left, so you guys can actually just have that up at all times. That should be very useful, and I hope you guys can kind of look at it side by side and make more sense of it. Okay, so I finished the first little section on that paragraph, or that section, so we're going to start right here. In general, this layer comprises the supported EM function of the tile as well as its operation principle. In particular, reflect array employs modifiable phase shifts applied over their surface. In the far field irradiation, reflected rays can be considered codirectional in their superposition constructive or destructive, is controlled by the applied phase shifts. Hence, wave scattering or controlled reflecting functions can be attained. Metamaterial tiles, however, operate as surfaces with tunable local impedance. Impinging waves create inductive surfaces or surface currents over the tile, which can be routed by tuning the local impedance across the tile. Notice that the Hewens principle, not sure what that is, I'll have to look into it, dictates that any EM wavefront can be traced back to a current distribution over a surface. As a result, in principle, metamaterials can produce any custom EM function as a response to an impinging wave. Common functions include wave steering, focusing, or collimating, i.e. producing a planar wavefront as a response to an impinging wave. Polarizing, phase-altering, full or partial absorption, frequency selective filtering, and even modulation. So now we're into the sensing section. Let me move this to the other side. There we go. Let's see. Here we go. The sensing and actuation plane. In order to control the EM waves per actual channel conditions, the programmable surfaces are expected to sense the propagation environment and actuate the upper surface plane accordingly. Such layer contains hardware elements that can be controlled to achieve a phase shift or impedance distribution across a tile. Commonly, the layer comprises arrays of planar antennas, such as copper patches and multi-state switches between them. Reflector array tiles usually employ pin diodes with controllable biasing voltage as switches. Metamaterials have employed a wider range of choices, both in the shape and geometry of the planar antennas and in the nature of switches. CMOS transistors, pin diodes, MEMS, microelectrical mechanical switches or systems, microfluidic switches, magnetic and thermal switches are but a few of the considered options in this literature. Notably, some options such as microfluid switches are state preserving in the sense that they require power only to change state but not to maintain it, i.e. contrary to biased pin diodes. Sensing and pinging waves are also necessary for exerting efficient control over them, while this information can be provided by external systems. With dynamic channels and mobile end users, tiles capable of incorporating sensing capabilities can be immune from the channel aging problem. The sensing can be direct, employing specialized sensors, or indirect, like an example, via deducing some impinging wave attributes from currents or voltages between tile elements. Now we're on to the third part on the computing plane here. The computing functionality serves the processing functionality in the controllable surface system. In the metasurface design in 60 and 62, FPGA-based controllers are connected to the metasurfaces to implement the computing functions. This layer comprises the computing hardware that controls the actuation and sensing elements. Its minimum computing duties include the mapping of local phase or impedance values to corresponding actuator states. Reflector array tiles commonly implement this layer using FPGAs and shift registers. Metasurfaces, and specifically HyperSurfaces, can alternatively employ standard IoT Internet of Things devices for the same purposes. That is worth highlighting. We'll do it in green. So, metasurfaces, and specifically HyperSurfaces, can alternatively employ standard Internet of Things devices for the same purpose, meaning anything that's in this Internet of Things can be used to do this manipulation that they need to do. Let me see if I think I do have the Internet of Things definition up here somewhere. Let's see. Yeah, here we go. Internet of Things is an arbitrary network of enhanced connectivity created by electronics, computers, and forms of communication, which entails, but is not restricted to, the internet and reduces human beings to nodes on a network whose sole function is to process the packets of bits and bytes of data being transmitted through the network according to protocols which have been established by those who govern the network. Okay, so there was protocols. We've got that. I will put a link to this album here. It's a series of images that you can access. Protocols. What are protocols? White papers, mandates, disguised, documented as official procedure. Juxtaposition 1 defines it as an illicit conspiracy formulated in secret by figures adhering to Swiss bank directives aimed at legitimizing illegal actions without public transparency or debate. That's exactly what's going on here. Okay, so back up. Here we go. We've also got the Internet of Bio-Nano Things. I'm not going to read it. I will probably read it in another installment to this series, but I'll let you pause if you want to read it. You can. Also have Internet of Medical Things. And with that, let's head back over to the main document. Okay. Moreover, metasurfaces, they can optionally include computing hardware elements, ASICs, distributed over the tile meta-atoms. This can enable an autonomous and cognitive tiles, where meta-atoms detect the presence and state of one another and take local actuation decisions to meet a general functionality objective. Nonetheless, these advanced capabilities are not required for programmable wireless environments. So that's interesting. They're not required. So that's probably something for us all to remember. So basically, what this last part is saying is that these meta atoms, again, these dead meta atoms, can detect the presence and state of one another. So basically, they can use anything on the Internet of Things, and they can detect each other. So basically, there is truth to the idea of being turned into a 5G antenna. I think there is a lot of truth to that, and I don't think that's a conspiracy theory anymore. I think we've actually just proved that because it's in this 6G white paper from 2020, and it's 2026 almost. Okay, let's see. Communications plane passes the signals from the processing layer to corresponding metasurface layer and collects signals from the sensing and actuation plane. In complicated programmable surface systems, communication occurs. Let me move this back over. Get myself situated. One moment. There we go. Cool. Okay, among planes to realize various EM wave control functions. The command signals normally operate at much lower frequencies compared to the ones emitted from programmable surfaces. Such signals prove to be more efficient in tuning the bias voltage of the pin diodes. This layer comprises the communication stack and connects the actuation and sensing layers, as well as the computing layer with tile external devices such as controllers. In the simplest case, this layer is implemented within the computing hardware, acting as a gateway to the external world using any common protocol, such as the Ethernet. Hypersurface tiles with embedded distributed computing elements additionally require inter-tile communication schemes to handle the information exchange between remember, SMART's an acronym, surveillance, monitoring, reporting technology, meta, dead atoms. So let me just translate that right there. It's very, very sneaky. Smart, meta, atoms. Anybody who really, doesn't know what I've told you, to just think, oh, it's just they're smart, they're very intelligent. No, smart meta atoms, smart surveillance, monitoring, reporting technology. Meta, dead. So spyware, hell, dead atoms. Great. Sounds great, guys. Future is going to be wonderful. Both wired and wireless intra-tile communication is possible. In both cases, the ASIC hardware employs custom and non-standard protocols. And then now we're going to get into use cases of intelligent environments. And I'm going to go ahead and put that image away. I will include it on the post on Substack so that you can download it or you can save it, whatever you wish to do. Use cases, okay. With the utilization of well-coordinated tiles in the intelligent environments, the wireless system can be greatly improved in terms of communication efficiency. 1. On-signal propagation enhancements. From the perspective of multiple users and moving users, the intelligent environment system is envisioned to serve a large number of users with more realistic user patterns, including mobile users and users in a cluster. Additionally, the intelligent environment system should ensure physical layer security against jamming and eavesdropping, unless it's from a fusion center by the government. An increasingly important problem that remains to be solved. Transmission distance. For the users in the NLOS areas, I wish I would have remembered or known what NLOS means. Areas relative to the transmitter, the intelligent environment system is expected to extend the transmission distance and reach previously uncovered areas through wave guiding or reflection. Simulation results in citation 67 demonstrate that at 60 gigahertz, the coverage can be extended to an entire NLOS area. Interference mitigation. Due to the scenario with multiple users, there is inevitably concern of interference. As in the envisioned scheme, each intelligent environment unit is dedicated to an individual user. Thus, the majority of interference will reside in the wireless section of the end-to-end link. I will highlight that. There we go. As in the envisioned scheme, each intelligent environment unit is dedicated to an individual user. Thus, the majority of interference will reside in the wireless section of the end-to-end link. Reliability. The primary efforts in terms of physical layer reliability include using highly directional antennas to nullify jamming, forming exclusion areas, assigning secret keys to legitimate users, and so on. From the perspective of fundamental propagation channels with intelligent environments, good reliability is achieved when the eavesdroppers do not have the knowledge of the frequencies where packages are transmitted, or the eavesdroppers are in the same frequency channel but with much higher noise, which makes the intercepted data impossible to decode. Therefore, the dedicated links in intelligent environments are inherently secure. So that first section that I just read was on signal propagation enhancements. The next one is on physical layer security. Let's see. Okay. The more frequent data exchange between users and service providers exposes a higher risk of personal and private data leakage. The 6G wireless network should not only inherit existing network secrecy measures, but also provide enhanced physical layer security associated with new enabling techniques. And current 5G networks, highly directional beams are used for wave communications, millimeter wave communications, in spatial domain to prevent signals from being intercepted. However, a recent study has shown that such pencil-sharp beams are still vulnerable to agile eavesdropping. Other physical layer encryption algorithms, including source coding approaches such as low-density parity check (LDPC) code, are demonstrated with optimal performance under specific conditions. Furthermore, existing solutions in the reconfigurable intelligent surface apply reflect arrays, which do not have the capability to effectively distinguish target users from malicious attackers. Hence, a solution based on the intelligent environment serves the purpose of identifying unintended recipients, creating null areas, and improving link secrecy rate. Essentially, the envisioned intelligent environments have the capability to sense user locations and exchange such information with a system controller to verify the user's authenticity. That's going to be great. So to verify you, they will just have to check in with Big Brother to make sure it's okay. Cool. Only affirmative users shall be served with signal streams from the sender. On the other hand, connection requests from unauthorized users, i.e. eavesdroppers, will be nullified from attempting to access secure information or even trying to establish links with the sender. In practice, the intelligent environments can be configured to tune the phases of multipath components in the channel, such that those arrived at intended users can be coherently combined with boosted received signal strengths, whereas those intercepted by eavesdroppers will be scrambled or even canceled due to non-coherent combining. Simulation results demonstrate a 6 dB attenuation observed at the received signal strength from the eavesdropper, validating the proposed physical layer security solution. Hence, the good channel secrecy is achieved when such unintended users do not own the knowledge of equalizer to recover transmitted signals from noise. Basically, I mean, to a degree, I kind of hear from that they are going to keep a lot of the specifics here kind of hidden or secret under the guise of security, obviously. But at the same time, it will kind of put people in a position where they have to rely on whoever these system controllers who will verify users' authenticity are. This is, I hope that the people who are watching this series understand, at least can see through the soft language being used. Because the fact that this paper is just using certain bits of soft language that I try my best to cut through is just so underhanded. Okay, so let's finish this off. The last subsection, open problems in intelligent environments. A number of open problems need to be addressed in order to facilitate the intelligent environments in becoming a market-ready solution. 1. Trade-off between dimensions and energy consumption. In terms of real-world applications, the intelligent environments are expected to be coded onto surfaces of interior walls or ceilings. Jesus Christ. Jesus Christ. Okay, 1 second. Let's highlight it. Read it again, just because sometimes you got to read things again to make sure you weren't make sure you weren't asleep. trade-off between dimensions and energy consumption. In terms of real-world applications, the intelligent environments are expected to be coated onto surfaces of interior walls and/or ceilings and building facades, which require dimensions that can both fit specific installation areas and satisfy link requirements. Meanwhile, with more reflect array elements and RF chains built into the system, the energy consumption will also increase due to the advanced signal processing circuitry. Therefore, how to achieve an economic solution, not like, let's just make sure people don't actually die from this first, because we're going to put it in everything, but let's make sure it's an economic solution first. Okay, continuing to balance the overall dimension and energy consumption while serving users to its desired performance is a non-trivial issue. Compatibility with existing solutions. Current Wi-Fi access points have a mature protocol stack to sense the channel and establish links with users. In order for the intelligent environments to assist with improving indoor signal coverage, it needs to be compatible with the IEEE 802.11 series standard. For now, this is still under research and serves as a worthy problem for novel solutions. Standardization. While many candidate approaches being investigated in reflect arrays, metasurfaces, frequency selective surfaces, among others, there has not been a consensus on how to standardize the device architecture. Maximum emitted power in communication protocols. As more ideas evolve, a standardization effort within a work group is necessary towards a solidary framework. So again, remember guys, this paper is from 2020, and they're talking about standardization. And this is before like AI hit the market like it has in the last couple years, which is really crazy to think about. Inclusion of advanced application scenarios as a promising solution for future generations of wireless systems. The intelligent communication environment should be designed to fit more advanced scenarios. For example, in use cases with a very large quantity of devices, as in the Internet of Things, under high demands of real-time video streaming with devices of high mobility, among others. Smart resource allocation solutions. Maybe that is a little bit of double speak, if you will. They could mean either way. But smart resource allocation means, doing it in an efficient way, or in a way, smart resource surveillance monitoring, to monitor people could be either way. But, seemingly they know how to use their double speak very well. So I would say that we should definitely consider it is both. Smart resource allocation solutions. Resources in the spatial, temporal, and spectral domains should be allocated in an optimal manner to satisfy per user demand. AI-driven, and I think that's what mesh, when they say mesh, I'm pretty sure it means that it can optimize and organize itself however it wishes to. AI-driven design and optimization in complicated scenarios under which no closed form solutions can be found using conventional optimization approaches. Advanced algorithms and artificial intelligence can assist in the development and deployment of intelligent communication environments, especially when complex surface layout or structures are in presence. Okay, and with that is section 4 on smart, intelligent communication environments, meta surfaces. So, guys, this is advanced. This is very advanced. It's to a degree there is a little bit of brilliance behind it, but with that said, all that goes out the door when you look at the track record and the history of the people who are using this and putting the money into it. Sure, this is amazing technology, but what does that matter when it's going to be used against us for malicious purposes without anybody being told about it? But guys, tomorrow we're going to do our weekly show with myself in juxtaposition, so I'm not going to do an entry into the series tomorrow, but Wednesday I will resume. So if you haven't seen the previous 3 parts, please check those out, and I will see you guys in the next one on Wednesday. Take care, guys.